Three pegs and disc, modeling using sequences. This is lesson 4 in topic 2 of module 1. Let's get warmed up. Write an explicit formula for each of the arithmetic sequences. Number 1, I notice that my first term is 9 and we are decreasing by 1. So my common difference is -1. So we can say 9 minus 1 times n minus 1. We could put that as our explicit formula. In the second one, my starting number is 20, and it looks like I'm increasing by 20 each time. So I'm going to start with my starting number is 20 plus 20 times n minus 1. Remember, n minus 1 is your previous term. The third one starts with 1, and we are increasing by 1.5 each time. And in algebra, we like to use improper fractions, so I'm going to keep that 3 over 2. So 1 plus 3 over 2 times my previous number, which is n minus 1. Our learning goals: model situations using recursive and explicit formulas, translate between recursive and explicit expressions of a mathematical model, explore the process of mathematical modeling. Key terms: mathematical modeling. If you've written recursive and explicit formulas for arithmetic and geometric sequences, how can you model a real-world situation using both recursive and explicit formulas for sequences? Let's take a look. Getting started. In this lesson, you will explore the process of mathematical modeling. The first step in modeling a situation mathematically is to gather information, notice patterns, and formulate mathematical questions about what you notice. Let's look over here. Mathematical modeling is explaining patterns in a real world based on mathematical ideas. Now we're going to play a game. You can either use 3 coins, a quarter, a nickel, and a dime, or you can cut out the circles at the end of this lesson. Pause the video to get your items situated. If you would like, you could stop this video and look at my other video pertaining to the coin trick. Let's play. The object of the game is to move an entire stack of discs or coins from the start circle to any of the other circles. The rules of the game are simple. You can only move one disc at a time, and you not put a larger disc on top of a smaller disc. Let's first play with 3 discs. To begin, place a quarter, a nickel, and a dime on top of each other in a stack, in a circle, or use the cutout disc at the end of this lesson to stack from largest to smallest in the circle. So again, I recorded me playing this trick in another video. Feel free to watch it. Play this game several times with a partner. Record the patterns that you notice. The second step in modeling practice is to organize your information and represent it using mathematical notation. Consider the question from the previous activity. Is there a relationship between the number of discs and the minimum number of moves? So if you notice in my video, when I had 1 disc, I had 1 move. When I had 2 discs, I made 3 moves. With 3 discs, I had 7 moves. So what do we notice about this pattern? the minimum number of moves for 3 disks is 1 plus 2 times the minimum number of the disk of the previous term. Use mathematical notation to represent the pattern you have identified in your results. So what we're going to do is we're going to write an explicit formula. Actually, we're going to start out saying a recursive formula. So we'll say dn represent the number of disks equals 2 times the previous term. 2 times the previous term plus 1 is our recursive formula. And you can also say n is greater than 1, assuming n is a positive integer. For 4.2, we're going to predict and analyze. Step 3 of the modeling process is to extend the patterns you created, complete operations, and make predictions and analyze the mathematical results. Use your results to extend the pattern in the table in the previous lesson. So we are multiplying by 2 and adding 1. So 7 times 2 gives me 14, add 1, that gives me 15. 15 times 2 gives me 30, add 1 gives me 31. Number 2, write a recursive formula to represent the pattern shown in your table. What predictions does this formula make for the minimum number of moves required for disk 4 and 5? So now they're kind of changing the verbiage to the minimum number. So we could write the minimum number of any term is 2 times the minimum number of the previous term plus 1. Assuming that n is greater than or equal to 1, assuming n is a positive integer. Number 3, write an explicit formula to represent the patterns shown in the table. So an explicit formula, m to the nth power, is 2 to the nth power minus 1. Assuming n is greater than or equal to 1, and n is a positive integer. So notice the difference between your explicit and your recursive. So let's analyze each one of these formulas. Let's say that I want to predict my third term. I already know it, but let's just pretend. So I'm going to plug in 3 for my third term. 2 to the third power is 8. Take away 1, that gives me 7. So that works. Here for my recursive, remember that's the previous term. So it'll be 2 times 3 plus 1. So that'll be 2 times 6 plus 1 gives me 7. (4.3) Test and interpret. The final step in modeling process is to interpret your results and test your mathematical predictions in the real world. If your predictions are incorrect, you can revisit your mathematical work and make adjustments, or start all over. Number 1, play the game again to demonstrate that your prediction for 4 disks and 5 disks are accurate. Record your observations. Then construct a graph to represent your explicit formula. Describe the characteristics of the graph in the terms of the situation. So our explicit formula is m to the nth equals 2n, 2 to the nth power minus 1. So if you notice, this is exponential. So we're going to show an exponential graph. I'm going to say that this bottom goes by ones, 1, 2, 3, 4, 5, and I should say my x-axis. And my x-axis represents the number of discs or coins, whatever you're using. My y-axis is the number of moves. And I'm going to have each one of these go by fives. 5, 10, 15, 20, 25. So if I just graph my table, I've got 1 and 1, which is just barely above that line. 2 and 3, just a little bit higher. 3 and 7. 4 and 15. 5 and 31. So that's 31. Hopefully you can see this exponential pattern. Suppose you can make one move every second. How long would it take you to complete a game with 25 discs? Show your work. So if we go back and use our our explicit formula, which is exponential, I would take n equals 2 to the nth minus 1, and I want to figure out the 25 discs. So I would put in 2 to the 25th power minus 1. Two to the 25th power, take away 1. So that would give us about a lot of moves. 33,554,431 moves. 1 second for every move. So how long is this going to take? Well, it's going to take that many seconds. If I divide by 60 to get the minutes, and then I divide by 60 again to get the hours, I would have like 9,320 hours. Divide by 24 to figure out how many days. So that would take me about 388 days to move 25 discs. Whew. Now, continue having fun modeling with your disc. Practice talk the talk. Complete the assignment at the end of this lesson. Also, look at the modeling process on how we model and interpret. We notice, we wonder, then we organize, we make predictions, we test, we may have to go back and organize, and then we make our report. Please email me if you have any questions.